Okay, picture this. You're standing at the edge of this massive body of water.
Mm-hmm.
And on one side, you have this bustling, chaotic city called client-side architecture. That's your iPhone, your laptop, maybe even your car.
Right, everything that you interact with.
Exactly. And then way across the water, you see the server-side architecture. These are just massive, silent data centers holding all the world's information.
And connecting them is a bridge.
A single, enormous, elegant suspension bridge.
It's a striking image. And if you look closely at that bridge, the traffic is just relentless. You get these huge trucks delivering heavy data, little sports cars zipping back and forth with requests. It all looks so seamless, almost like magic.
But it isn't magic. It's engineering. And that bridge, that is what we're deep diving into today. We're looking at the architectural style that, and this isn't an exaggeration, quite literally holds the internet together.
We're talking about REST.
We are talking about REST.
Representational State Transfer. It's one of those acronyms that gets thrown around constantly in tech. Is this API RESTful? Oh, we need to build a REST endpoint. But, surprisingly few people actually stop to understand the mechanics of why it works, or even where it came from.
Right. And we have a stack of sources today that are going to take us way beyond just the dictionary definition. We're going back to the year 2000 to a Ph.D. dissertation by a guy named Roy Fielding, which, let's be honest, sounds incredibly dry, but it really changed the world.
It did.
We're going to unpack the rules of the road, the big debates, and of course, the security implications.
Fielding is really the architect of that bridge you described. In his dissertation, he defined REST as an approach to create internet-scale, network-based applications. And I want to flag that phrase immediately.
Internet scale.
Internet scale. That's the key. We aren't talking about connecting two computers in a basement with a wire.
No.
We're talking about connecting billions of devices across unreliable networks with different operating systems, all trying to talk to each other at the same time.
So our mission today is to understand this universal adapter of the internet. I know we see a lot of buzzwords, GraphQL, gRPC, WebSockets.
All the new hotness?
And our sources acknowledge they're cool and useful. But the slides make it very clear. Today is about the incumbent, the industry standard.
Precisely. If you want to understand how the web scaled from, a handful of researchers to the global nervous system it is today, you have to understand REST.
So let's rewind to that origin story. You mentioned 2000. What was the web actually like before Roy Fielding laid down the law? Because I assume we didn't always have this elegant bridge.
No, we certainly did not. The sources describe the pre-REST era as anarchy.
Anarchy. That seems a little dramatic for computer science.
It's accurate, though. Imagine trying to connect different hypermedia systems, websites, databases, mainframes, but with no consistent rules. It was a tangled mess of these ad hoc connections.
So one system speaks French, another speaks Klingon.
Exactly. And if you wanted to build an integration, you had to manually wire everything together. It was incredibly fragile. If one tiny thing changed, the whole system could break.
I'm looking at a visual in our notes that shows this progression. It starts as this scribble of lines, just a chaotic knot.
Yeah.
Then it moves to a grid, showing a desire for order, and finally it resolves into this clean honeycomb structure labeled REST architecture.
That honeycomb represents the ultimate goal, anarchic scalability.
Okay, anarchic scalability. That sounds like a contradiction in terms. Usually anarchy means things just break.
It does sound paradoxical, doesn't it? But here's the brilliance. The goal was to engineer a system that could function under totally unanticipated loads, like a viral video hits.
Or Black Friday shopping.
Right. While allowing every little component to be deployed independently. You don't want to have to shut down the entire internet just to update one server in Kansas.
So to achieve this order out of chaos, Fielding proposed what the notes call the architectural triad. It seems like these are the three pillars holding up our bridge.
Yes, the triad. I like to think of them as the noun, the address, and the vessel.
Let's unpack those. First, the noun. This is the resource, right?
Correct. In REST, we stop thinking about actions and we start thinking about things. A resource is anything that can be named. A user, a photo, a blog post. We identify them with media types like application JSON. It's the what we're talking about.
Then we have the address, or the URI. That's what sits in the bar at the top of my browser.
Exactly. The URI specifies the protocol and the location. If you look at the example here, t.example.com.edu blog 2025 search. It's a very specific set of instructions. You have the scheme, the domain, the port, the path.
And even query parameters at the end, like .tag_appy.
Right. Think of the domain as the building, the path as the filing cabinet, and the query parameters as the specific folder inside that cabinet.
And finally, the vessel, that's HTTP.
That's the application layer protocol. These are the trucks driving across the bridge, carrying the resources to their addresses.
So we have the what, the where, and the how. But just having the parts isn't enough. You need rules. And this is where it gets really interesting. The constraints of internet scale. The notes show a hexagonal diagram with 6 constraints. These aren't just suggestions, are they?
No, these are the non-negotiables. If you want that internet scale success, you have to follow these rules.
The first one seems pretty straightforward. Client server.
It sounds obvious now, but it's all about separation of concerns. The client, your phone app, should worry about the user interface. The server should worry about data storage and security. This allows them to evolve independently.
Okay, but the second one, this is the big one. Our notes have it highlighted in red. Stateless.
This is the critical rule. The server holds no session state.
Okay, let's break this down. Because stateless sounds a bit like the server is just lazy. What does that mean for me as a user?
It means the server has amnesia. Every single time you send a request, you have to include all the context the server needs to understand you. The server doesn't remember, oh, this is the guy who asked for a photo 5 seconds ago.
It treats every request as a brand new interaction.
A completely new interaction.
That sounds incredibly inefficient. Why would you want the server to forget you? Wouldn't it be faster if it remembered I was logged in?
It might seem faster for you if there were only, say, 10 people using the app. But remember, internet scale.
Right.
If the server has to remember the conversation history for 10 million users, its memory fills up and it just crashes. But if it's stateless...
Oh, then any server can help me.
Bingo. If server A crashes, server B can pick up your next request instantly because it doesn't need to know what you and server A were talking about.
Ah.
You bring all the context with you. It's a huge insurance policy for reliability.
That makes total sense. So we pay a little tax in carrying our own data to get massive reliability in return. What about cacheable?
That's the efficiency counterbalance.
Yeah.
Responses have to explicitly say if they can be saved for later. If you request a company logo, the server says, here you go, and by the way, don't ask me for this again for 24 hours.
Got it. Stops us from clogging the bridge.
Exactly. And then you have layers system, which is a bit sneaky.
How so?
Because the message is self-contained, the client doesn't need to know who it's actually talking to. You think you're talking to the main server, but you might actually be talking to a load balancer, which talks to a security gateway, which talks to a cache, which then talks to the server.
And as the client, I have no idea.
None. And you don't need to. That lets engineers add layers of security or performance improvements without ever breaking your app.
Before we move on, let's trace the life of a request. We think click button, get data, but there's a whole physics to this.
There really is. It starts with DNS resolution, turning the name into a number, but then comes the dance, the TCP handshake.
Ah, the SYN, ACK dance.
It's a very polite dance. The client sends a SYN packet basically saying, hello, are you there? I want to talk. The server replies with SYN ACK. I see you, and yes, I'm listening.
And finally, the client sends ACK. Great, here it comes.
And all of that happens before a single byte of your actual data even moves.
Every single time.
Every single time. Unless you're using a persistent connection. That's why latency is such a performance killer. It's not just the data travel time. It's all that polite introduction time.
So the bridge is busy with a lot of hand-waving before the trucks even start moving.
Yeah.
Okay, let's shift gears. We've got the basics, but apparently not all APIs are created equal. The sources talk about maturity.
The Richardson maturity model, yes. This is the yardstick we use to measure how restful an API actually is. It has 4 levels.
Starting at level 0, which is called the swamp of POX, plain old XML. That doesn't sound very inviting.
It's some developer humor, for sure. The swamp of POX is from the old days. You're using HTTP, but just as a tunnel. You have one address, one method, usually pusevt, and you just shove a massive, ugly XML blob through it.
It's like using a Ferrari to deliver the mail. You're not using any of the car's features, you're just using it as a box.
Perfect analogy.
Yeah.
Then we step up to level 1, resources. Now we're getting somewhere. We have distinct addresses, users, products.
But still just one method, probably.
Probably. But level 2 is where the notes say the industry standard lives.
Yeah.
This is where we start using HTTP verbs correctly.
Right. You use get to retrieve, post to create, delete to remove. And you use proper status codes 200 for, okay, 404 for not found.
This is where most real-world APIs you love. Stripe, Twilio, they all live at level 2.
But there is a level 3, the purest level, hypermedia controls, or HATEOS.
HATEOS. Hypermedia is the engine of application state.
I feel like you win a prize just for memorizing that acronym.
It's a mouthful, but the concept is actually beautiful. It means the API response tells you what you can do next.
Can you give me a real-world example?
Sure. Imagine you request an order status. A level 2 API just gives you the data, status, shipped, end of story.
Okay.
A level 3 API gives you the data, plus a section probably called links. And in there, it might give you a link to track order or cancel order or return item. The API gives you a dynamic menu of what you can do next.
It's like a choose-your-own-adventure book built right into the code.
That's a perfect way to put it. It makes the API self-documenting.
Okay, but here's where I have to push back a little. If level 3 is the ideal, why isn't everyone doing it? The source mentions a great debate here.
It's a huge debate. The pragmatists people at Google, Meta, they argue that level 3 is often overkill. Building that choose-your-own-adventure engine is complex. It adds weight to the response payload.
And if you control both the app and the server, you already know the next steps. You don't need the server to tell you.
You got it. For internal APIs especially, the overhead often outweighs the benefits. So being restless at level 2 is usually good enough.
Restless. I like that. So assuming we're building for that level 2 sweet spot, let's talk strategy, naming and verbs.
The grammar of the web.
The rule for URLs is use nouns, not verbs. Why is that?
Because the URL is the address. It
Oh.
identifies the thing. The verb, the action comes from the HTTP method itself. So you shouldn't have a URL like get cities or create city.
Why not? It seems pretty clear.
It's redundant. The getET method already says get. If your URL is get cities, you're basically saying get cities. It's just messy. You want cities. Then you send a get to read it or a post to add to it. The verb is separate from the noun.
That makes sense. But what about when things change? If I change the city's endpoint, don't I break the app for everyone using the old version?
That is the nightmare scenario, and that's why you need a versioning strategy.
The notes mention 3 ways to do this. Path-based.
That's the easiest and most common. You just put it right in the URL, open one cities, make a breaking change. You launch a puff 2 cities. The old apps keep using V1. New apps use V2.
Seems safe. The purists probably hate cluttering the URL, though.
They do. They prefer header-based versioning. You keep the URL clean just cities, but the client sends a hidden header saying accept version in V1. It's cleaner, but harder to test.
Let's talk about the verbs again. CRU. Create, read, update, delete. There's a concept here that always trips people up. Idempotency.
You and every other developer. But it's a crucial safety concept.
So help me out. What does idempotent actually mean in plain English?
It means that making a request 10 times has the exact same effect on the server as making it once.
Is it like calling an elevator?
Perfect analogy. You press the call button, the light goes on. You can press it once, or you can mash it 50 times because you're late. The outcome is the same. The elevator is called exactly once.
So which REST verbs are elevator buttons?
Put and delete are elevator buttons. If I send a delete request for a photo 10 times, the result is the same. The photo is gone. The server doesn't error out. It's safe to repeat.
And which ones are in the danger zone?
Post. Post is not idempotent.
So if the elevator button is delete, what's the post button?
The post button is a vending machine. If you put your money in and press Snickers, you get a Snickers. If you get a patient and press it again,
I get 2 Snickers.
and you just paid for 2 Snickers. That is the danger. If you retry a POST request to a banking API because your internet was slow, you might accidentally transfer money twice.
That is a terrifying thought.
It is. It's why developers lose sleep over POST.
There's another nuance here between PUT and PATGH. The note says PATGH is often preferred. Why?
Think of PU as replace. You're sending the entire file again. If you put a user record but forget to include their email address, the database assumes you want the email to be blank. It wipes it out.
Ouch. And PATGH.
PATGH is modify. You
Yeah,
just
yeah.
say change the email field to this new value and leave everything else alone.
Yeah.
It's much, much safer for partial updates.
Speaking of mechanics, let's look at controlling the flow. Pagination. We can't just dump a million records onto a phone screen.
No, you'll crash the app. You need to break it into chunks. The sources contrast offset-based versus cursor-based.
Explain the offset problem to me. Give me the next 100 items. Why is that slow?
Imagine a million-page book. Offset is like saying skip the first 500,000 pages and read the next one. To do that, the database actually has to flip through and count all 500,000 pages just to know where to start. It gets very slow. very fast.
And cursor-based.
Cursor is like a bookmark. You just say, start reading right after the bookmark I left last time.
Yeah.
You don't care how many pages came before. You just open it and go. It's instant.
Huge difference for infinite scrolling. Now, I want to touch on partial responses. This is preventing overfetching.
Right. Sometimes you ask for a user, and the API gives you everything. Name, age, shoe size, favorite color. But your app only needs the name. That's a waste of bandwidth. Partial responses let you say, field's name, T-bar cheese. Just give me what I need.
And deletion strategy. This one surprised me. Hard delete versus soft delete.
A hard delete is what you think it is. The data is gone forever. 404, not found. A soft delete is more polite. It just marks the data as inactive in the database.
So it's still there.
It's still there,
Yeah.
but the API pretends it isn't. This is crucial for things like legal compliance. If a user deletes their account, you might still need to keep their transaction history, so you soft delete the user.
Let's move to security. The slides highlight stateless security using JWT JSON Web Tokens.
This ties right back to that stateless constraint. Since the server has amnesia, it doesn't remember you logged in. So you have to present your ID card with every single request.
And the JWT is the ID card.
Exactly. It has a header, a payload, which might say this is user 12345, and a cryptographic signature.
But there's a giant warning label here in the notes. Must be used over TLS, HTTPS. Why is that so critical?
This is a common misconception. A JWT is usually just base64 encoded, not encrypted.
What's the difference?
Encoding is like translating English into French. Anyone with a dictionary can translate it back. If I steal your JWT, I can easily decode it and read your data.
So if I send that over plain HTTP...
Anyone listening on the coffee shop Wi-Fi can steal it, decode it, and impersonate you. It's like walking around with your passport taped to your forehead. You need that encrypted tunnel of HTTPS to hide it.
But wait, if I can decode it, can't I just change the user ID from 100 to 1 and become an admin?
You can try. But that's where the signature comes in. It's like a wax seal stamped by the server. If you tamper with the payload, the seal breaks. The server checks the math, sees the seal as broken, and rejects the token.
Got it. Math saves the day. Before we wrap up, the contract, the OpenAPI specification.
This is about professionalizing the process. Instead of just writing code and hoping people figure it out, you write a contract first. It's a machine-readable document that describes exactly how the API works.
And this allows for contract-first design.
Yes. You write the contract, and then tools can automatically generate the code for the server and the client. It keeps everyone honest and aligned.
So we've crossed the bridge. We've seen the rules, the vocabulary, the mechanics. Let's look at the scorecard. What are the wins and costs here?
The wins are massive. Scalability, we can handle the whole world. Cacheability, it's fast. Interoperability, it's a universal language.
But the cost?
Overfetching and underfetching, it can be chatty. Sometimes you have to make 3 round trips across the bridge to get all the data you need for one screen. That's inefficient.
And that's actually where things like GraphQL have started to gain traction, right? To solve that specific chattiness problem.
Exactly. But for the vast majority of traffic, that north-south traffic from a client to a data center REST is still the undisputed king.
The final visual here returns to that metaphor. It calls REST the universal adapter of the internet.
It's a great closing image. Think of those chunky international travel adapters. They aren't always the sleekest, but they allow you to plug anything into anything, anywhere in the world.
While GraphQL might be the slick new charger for your specific phone, REST is the thing that works in every hotel room, from Tokyo to New York.
And if we connect this to the bigger picture, REST favored resilience over pure efficiency. Those constraints, statelessness, the uniform interface, they are exactly what allowed the web to grow from a few university nodes to the global system it is today.
That's a powerful thought to end on. We often obsess over optimization and speed, but sometimes resilience, just knowing the bridge won't fall down, is the most important metric.
Absolutely. And remember that debate between the purist and the pragmatist. We as developers often strive for architectural perfection, that level 3, fully discoverable system. But the biggest systems in the world succeed by just being good enough at level 2.
So perfection isn't the goal, connection is the goal.
I think Roy Fielding would agree with that.
Thanks for deep diving with us into the architecture of the internet. Hopefully the next time you see a URL, you'll see a little bit of that magic and the handshake dance holding all together. Catch you on the next one.
Goodbye.